right, getting into section 6.4, a little over halfway through the chapter now. So we are going to introduce you guys today to something called polar coordinates. What we are used to, of course, is rectangular coordinates. So rectangular coordinates have an x value and a y value. But when you get to polar coordinates, your first value represents the radius, and your second value represents the angle. Okay, and I'll show you that comparison down below on the notes here in just a second. But first I want to look at graphing polar coordinates, and so get you guys some kind of a visual of how this would work. So here's our polar coordinate graph, right? Obviously the same type of values we've seen on like the unit circle, right? We got our 0 degrees, 90, 180, 270. A lot more angles have been filled in onto this just so you could see them all. But here's kind of one of the biggies, is we are not only using the angle to figure out where we rotate around the circle, but we are also using the radius to see how far away from the center we are. So there's kind of two things at work here. So let's just look at the first one. So if my radius is 2 and my angle is pi over 3, which of course is 60 degrees, so you could look at this either way. So I know that I need to be 2 units away from the center, and this is a positive 2. So as I start, I want to use that radius first. So if it's positive, I want to go to the right. If it's negative, I want to go to the left. So this one is a positive 2, so I'm going to go out 2 units to the right. So this would be a radius of 1, and this would be a radius of 2. So it starts right there. And now I want to go 60 degrees or pi thirds in the counterclockwise direction. We still move counterclockwise just like we've always done with trig, unless you get the negative, and then this would tell you to go in the clockwise direction. So same thing as we've been doing with trig and unit circle all along. So again, I went out 2 units, that's my radius, and now I want to travel a positive 60 degrees or pi thirds in the counterclockwise direction, which would put me right there. So my point A would be this guy right there. And there's our first point. One thing I do want to point out to you guys is, and you've seen this with other things within trig as well, but there's obviously different values I could use that would still put me in the same location, right? Specifically when I change the angle of this. So just like I went right 2 and then I traveled 60 degrees in the positive direction, well, I could also go right 2 and travel negative 300 degrees in the in the clockwise direction, and that would still give me the same point. So do recognize that I can use other ordered pairs to represent the same point on this graph. Right? There's more than one way to get there. So just keep that in mind. Let's take a look at this guy right here. So this one now has a radius. I'm trying to give you all the different looks I could mix and match in here with the negatives. So this one now has a negative 3 for the radius. So that just simply means I want to go left 3 right there to start. And then I'm going to travel from there. I want to travel 150 degrees in the positive counterclockwise direction. So from here, I'm at 180 essentially, right? So I need to add 150 onto that as I travel around the circle from here. So I'm really looking at, if I go 150 degrees from here, so starting at my radius at negative 3, if I add 150 onto 180, that should land me on 330. So this would be our spot for point B. It would look like this. So what if our radius was 4? And notice now we're now traveling in the negative direction. So if I go right 4, since it's positive 4, so we got a radius of 1, 2, 3, 4. So I'm starting right there. And now I'm going to travel negative 90 degrees. So that means I need to go clockwise 90 degrees. And so if I did that from my starting point, should put me right there for point C. And again, guys, notice there's more than one way to identify that point, right? Point C could be called 4, negative 90. It could be called 4, positive 270, would also put me on that same point, right? And not to mention, I could keep adding 360 onto this forever. So there's like an infinite amount of points that would give me the same position on the graph. Let's do one more. So both negative. So this one is now starting at -5, which means I need to go left 5 to begin this process. So 1, 2, 3, 4, 5. So I'm starting right there. And now I need to travel. And guys, remember, negative just means go in the clockwise direction. Positive means counterclockwise direction. So from my starting point, I need to go negative 45 degrees, or pi over 4. All right, so from here, if I travel, subtract essentially 45 degrees, should put me right here is my value for D. And so that's how graphing these guys work. So now that you've seen that, let me write the connection here. So again, guys, we're of course used to seeing rectangular coordinates. That's just your typical coordinates that we put on what we call the Cartesian plane, which is your XY axis, right? So those are like the most basic points that you first learned when you're much younger. So we are now simply translating those into polar coordinates because we have a radius and an angle instead of simply an X and a Y. Do keep in mind, all this is going to have like some conversion type formulas to them. This is still true. It's always been true. One thing we want to recognize within this, though, is as we've been doing trig stuff all along, the X value on the unit circle has always represented our cosine function, and the Y value has always represented the sine function. Tangent has always been sine over cosine. So all that is still true. This is kind of your conversion between the rectangular coordinate to the polar coordinate, right? This is how we convert this. So R is for radius, of course. So your X coordinate is going to be R cosine theta, and then your Y coordinate is going to be R sine theta, right? And this is still tangent. So let me flip this over. And let me take you guys to this one. All right, so take a look at the first one. I added something in here because I wanted you to see kind of the difference on this is when we are converting from polar coordinates into rectangular coordinates, there are certain ones that we can do by hand, and there are certain ones that we cannot do by hand because simply they're not on the unit circle. Like 80 degrees is not represented on the unit circle. However, 3 pi over 4 is. Right, and so if possible to do it by hand, we want to do this by hand. But when it comes to a case like this where it's not on the unit circle, then we may have to use a calculator for that. So I wanted to start you guys with, was their first example, but I wanted to show you that introduction first. So let me show you theirs, and then we'll do those 2 practice ones on our own. So here they're giving us, obviously, polar coordinates because of the angles that are represented right here. It's clear to see that these are polar coordinates, which means the 4 and the 5 represent a radius, and these guys represent the angle that we're traveling, just like we showed in the graph on this. So let me show you sort of their process for doing this, and then we'll try those practice ones together. So here was the first point. This was A. So again, radius is 4. Theta, the angle is 2 pi over 3. And this is what we saw within those conversion formulas just a minute ago. So if I want to get my x coordinate, I simply plug in these values into this formula right here. So 4 is going in for r, the angle is going in for theta, so that it looks like this. And now this is something that I can get from my unit circle. If we find 2 pi over 3 on the unit circle, the cosine of 2 pi over 3 is negative 1/2. So that's going in for this guy. I'm just bringing down the 4, and as I multiply those together, it gives me the x coordinate. And we're going to do the same thing for the y coordinate, except it's now the sine value, right? So slight change in the formula. When you want the y coordinate, we're going to use r sine theta. And again, I'm just plugging in the numbers. The sine of 2 pi over 3 is rad 3 over 2. Multiply that by our radius, and you got your value right there. Now, we could leave this in an exact form, right? I could just clean that up and call it 2 rad 3, and that's fine if we leave it like that. You know, if we want to go decimals, we can. Typically, we want to just follow directions if they specifically tell us which one to do. Usually I'm sort of a fan of keeping things in exact form, unless the directions specifically tell me to round. Anyway, so let's look at the next one. So for the second point they gave us, I got this radius of 5. Here's my angle. So notice on this one, 75 degrees is not represented on the unit circle. So here's one we would need a calculator for. Be careful on whether you're in degrees or radians, right? Obviously, this would have been a radian problem, and this would have been a degree problem. So if we are using calculators on this, just be careful as to which mode you're in. So we're going to plug in that 5 for r. We're going to plug in negative 75 for theta, and we're just doing straight calculator to get the x value. And then we're going to do the same thing with our y value, but using the sine function. Here's your radius, here's your angle, pure calculator, get you the y coordinate. And so we can write that as an ordered pair. And now we have rectangular coordinates. So let's try. So actually, let me just show you guys this real quick. If you look at the solution set that we got from the first one, all right, so this was the first one that we did up there. From the very first problem, they told us that the x-coordinate was -2. That's what we figured out. And the y-coordinate was about 3.5. So notice on this one, if I went left 2 and up 3.5, it still puts me on the same position on this grid as if I were doing the polar graph. Right? The polar graph had a radius of 4. So it went right 4, and then it traveled 2 pi over 3 to get to that point right there. So if you were to graph both, you should still find yourself landing in the same position on the graph. And that's always a way of sort of checking to make sure that we did it right. Here was the other one that they did. So the second one that we just did up top here, notice and I guess this is why there would be a benefit in using decimals to help you plot these on a graph. So if I go right about 1.3, which they're saying would be about here, and then I travel down 4.83, so if I go down 4.83, it gives me this point right here, which is Q, and I would get the same value on my graph if I were to graph this with the polar coordinates. So the polar coordinates for this problem were 5, -75 degrees. So if I went right 5, and then -75 degrees, it still puts me in the same location. So we can always verify that by a graph if we did that correctly. So let's practice a little here, and you're welcome to pause and try these ahead of me. But again, as I look at this, to get my x-coordinate, I want to use the formula r cosine theta. So my x is r cosine of 3 pi over 4. And so what is the cosine value of 3 pi over 4? We know that's going to be negative rad 2 over 2. So if we clean that up, I can replace cosine of 3 pi over 4 with negative rad 2 over 2. And again, I would just leave this in exact form unless you're actually trying to graph it, because if you do want to put it on the graph, decimals are easier. But just for now, we don't have to type this out. We can leave it in exact form. So let's call this negative 3 rad 2 over 2. So there's our x-coordinate. Let's try the similar formula for the y-coordinate using the sine function. So for y, we're going to say 3 goes in for the radius, and now I'm looking at the sine of 3 pi over 4, which we know the sine of 3 pi over 4 is just positive rad 2 over 2. So multiply those guys together, and we have our y-coordinate. And of course, we could put those together and write that as an ordered pair. I'm just running out of space. So let me jump down to this one. So again, guys, when you see an angle like 80, you can't do that by using the unit circle. So we'll have to use a calculator for this. So let's just plug it into the formulas. So on this one, I'm looking at 6 cosine 80, which we're just going to throw into calculator, make sure I'm in degrees. So 6 cosine, and I have my x-coordinate about 1.04. And let's do the similar formula for y. 6 sine 80. Again, we got to do calculator on this one. So 5.91 would be the y-coordinate. Okay, so fairly simple, just formulas, use of formulas for doing those guys. So what if we wanted to go the other way? What if we wanted to go from rectangular to polar? So take a look at the formulas that we've already been talking about here. One thing we want to put to use on this one is we need to figure out what that radius is, right? And so that's kind of the first step in the process, is just figuring out the radius that we're dealing with. Because we know when we write these in polar coordinates, this is the radius and that's the angle. So we got to find both. So we're just going to start by finding the radius using this formula that we're all familiar with. So plugging in the 1 for x, plugging in the 2 for y, real simple, getting this guy right here. Right, so we have our radius, could be positive or negative, root 5. So how do we know if we should use a positive or a negative for our radius? And that's the side note that I wrote right here, is look at what quadrant this would put you in, right? And that's going to help us determine whether things are positive or negative. So if I went to the point 1, 2, in other words, right 1 up 2, I know that puts me in the first quadrant. So keep that in mind. Our value here should be in the first quadrant. As we go through this process, so we looked at the graph a minute ago. So for me to go right 1 and up 2 means whatever I come out with for my radius and my angle needs to put me in that same position when I go to write my answer for this. So what they used to get the angle was the tangent formula that we showed on the previous page. So we know tangent is y over x, or sine over cosine. So they just plugged in the numbers for y over x. So tangent of theta equals 2. Of course, we would do inverse tangent of 2 in order to get the angle. Now in this one, they chose to do it in radians. I think it's a little easier to visualize where this is going if we do it in degrees. So if you were to do this in degrees instead, it's about 63.4 degrees. So there would be our angle. And so if I really wanted to now put these together, so I need a radius and I need an angle. Well, if my angle is 63.4 degrees and my radius is the square root of 5, let's just see that as a decimal for a minute, which is about 2.2. So in order for me to get to this position right here, they're telling me they want me to go 2.2 to the right, that's my radius, and then travel 63.4 degrees to get to here. So according to that, would it make sense for this to be a plus or a minus? Right? Only the positive would make sense for this. So we're going to say positive rad 5 is our radius. So we are looking at that position right there. So just to make this a little more fun, they do want us to write two answers for this. So they do want us to write the one where we use the positive radius, but they also want me to look at the one where I use the negative radius. So what if we had gone negative rad 5? Because as we've already seen, we can write this in many different ways and still land us in the same position, right? So instead of going right rad 5 and then travel that way, what if we went left rad 5? How much more would we need to travel in order to get to that same position? So had I gone left rad 5, I would have to go 180 degrees plus another 63.4 degrees to get to here, right? So if I look at this one, essentially I'm adding 180 degrees onto this in order to get that answer. So let's see, 180 plus 63.4 would be what, 243.4, I believe? So two different ways we could write this. We could write this with a positive radius, which is definitely the easier route to go. But had we used the negative radius, that's fine. We just have to add another 180 degrees onto that in order to get to this. Now, they show it in radians. So just keep in mind, instead of adding 180 on to this angle, they would have added pi onto this angle in order to get this point right here. So if you took your 1.11 and just hit plus pi, it's going to give you the same answer but in radians rather than in degrees. And so that's what you're seeing on this page right here. So if you took this and just hit plus pi, you'll get their second answer that they use right here. So those are the two angles they wanted us to show with a positive and negative radius. Let's take a look at one more of these. Which, by the way, I guess let me just show you. So here was the graph that we were just talking about, right? So, and we kind of already laid all that out, so we know we're in good shape. Here's the graph for the one that we're going to look at right now. So what if the point was 4, negative 4? I'm going to try to get all this on the screen for you as best as I can. Actually, I'll do this, watch. There we go. So here's our point right there. So we're using the point 4, negative 4. So of course, when we look at the graph on this, 4, negative 4 is in quadrant 3. So whatever I do as far as positives and negatives go, I want to make sure that I end up in quadrant 3. Right? And that's how I know that I'll get the signs right. So let's just do this one in radians so that you guys can get a little practice with radians as well, even though they might be a little less obvious than the degrees. But again, here's the formula that we're going to use to get the radius. All right, so here's their radius right here. So again, it's plus or minus, so we're looking at the two possible ways that we could write this with a positive radius and a negative radius. Keep in mind, as we've already seen, there's many different ways you can write these and still get the same answer. Okay, so here's what they did on this one. Is they said, well, if our radius is 4 add 2, so in other words, I have to go right 4 add 2. So in my first scenario, how do I get from here to here as far as an angle goes? Right? And so there's really two ways you could write this. I could write it by saying, well, I'm just going to travel in the negative direction, or I could look at it as I'm going to do this and go all the way around and get to here. They would both be correct, really. So in this one, they're trying to use the smallest values possible. So for the first one that we're going to look at, they said, well, we're going to travel in the negative direction and take the short route. Right? And so that's where they're coming up with this answer. So remember how we get the angle? So tangent is y over x, so the y coordinate over the x coordinate. If you do the inverse tangent of negative 1, then we would get negative pi over 4. Now, for this one, they obviously didn't use the calculator. They said, this is an angle that we know. Right? I know that when I look at my unit circle, tangent values, where I would see negative 1, would be this angle right here. Right? This angle has a tangent value of negative 1, and this angle, 3 pi over 4, would fit that description as well. So those are the two angles that they're using on this. So again, they kept these in exact form because this is something we know from the unit circle. So they figured out that the angle is 3 pi over 4, and again, guys, they did not have to say negative pi over 4. Right? That's not required. You should recognize that this is an accepted answer. However, if you would have gone this direction around, right, then what angle would that be if you went in the positive direction? So instead of saying I'm going to go negative pi over 4, we could have said I'm going to go positive 7 pi over 4. And that would work too. What this goes back to is the whole idea of that one-to-one function that we looked at a couple chapters ago, where, you know, if you actually put the inverse tangent of negative 1 in your calculator, it's going to give you a negative, this negative angle right here. So this is actually the calculator answer that we would get, right? That's the initial standard value that we would get. So if I did, let me just go to radians for a minute. So if I do the inverse tangent of negative 1, so this is negative pi over 4. Right? Same value. So the reason they're using this as the initial angle goes all the way back to that one-to-one function idea that we talked about a long time ago, where tangents and sines both give you initial answers in these areas right here. Right? It goes from 0 to positive pi over 2, and it goes from 0 to negative pi over 2. So that's the initial answer that they're going to give you. And so if you were to, check answers in the back of the book and things like that, this is what you'll find, right, is the initial answer. So, so if that's the initial value that I'm going to use, well, what if, instead of going right 4 rad 2 and then this way, what if we went left 4 rad 2? How do I get from here to here? So what would I have to add on to this in order to get from this position to that position? So remember what we just did up above on the previous one is when I have this value, right, I can add pi onto that to get me this same angle. So if you did negative pi over 4 plus pi, that's going to give you this exact same position. So negative pi over 4 plus pi. So if I just hit plus pi, is going to give me that angle right there, which is 3 pi over 4. So in other words, if I went negative 4 rad 2 and then 3 pi over 4 radians, it would land me right there. So what they're trying to show you right here is the equivalent angle, right? So we know that 3 pi over 4 looks like this, right? It's 3/4 of pi. So if I was right here and I travel 3/4 of pi in the positive direction, it's going to put me right there. So these are the two most appropriate ways to write these answers, even though we've shown there really are other ways you could write it. These are the two initial ones that you're going to find as kind of the main accepted answers to this. So let's jump down to this guy. Let's try one on our own here. So notice on this one they are giving me a specific domain on this, and I'm really glad when they do this because then it helps eliminate other possible answers. Like you just saw in the previous one how there was many different ways I could have written that, and they all would have been right because they didn't give a specified domain. So by doing this, now they're limiting us and helping to guide our answers into the way that they want us to write them. So I'm really glad when they give us a domain like this as a guide. So first things first, keep in mind if we were to plot the point negative 3, 3, we would definitely be in quadrant 2. So there's our point P, negative 3, 3. So I want to make sure I end up in quadrant 2. With all the ways that I write this answer. So they're giving us these values right here. So remember how we started this. We know that r squared is equal to, x squared plus y squared. So 9 plus 9 is 18. So our radius is the square root of 18 plus or minus, which they're going to want us to simplify that. Let's see, that would be 9 times 2, so 3 root 2. So we're going to say the radius is plus or minus 3 root 2. There's our radius. So now we just need to find the angle. So remember the way they did that was the inverse tangent of y over x. So we're going to use the inverse tangent of 3 over negative 3. Which of course is negative 1. Let's just type that in. So we already know what this is going to be. It's the same one as what we just saw in the last problem. So if you type in the inverse tangent of negative 1, or just look at it on the unit circle, remember the initial response that we would get from a calculator, as we just talked about, would be, of course, it's a decimal, but it's the same decimal that relates to negative pi over 4. Right? This is the initial angle that a calculator would give you. So let me bring you back to this drawing for a minute. So the initial value that I get from a calculator is going to put me right here at negative pi over 4. However, for this problem, we know that's not where we are. We are in quadrant 2. So I need to adjust by saying, hey, I don't need to be at negative pi over 4. Let's add pi onto this, which is going to be 3 pi over 4, and that's going to be our initial angle, is 3 pi over 4. So let me just write it this way. So we recognize 3 pi over 4 is what puts me here. Negative pi over 4 would put me here, and I know that's not the quadrant I'm in. So I want to use an angle that's going to land me in the proper quadrant. That's also why in this problem, notice the way they wrote this domain. It goes from negative pi to positive pi. So they want me to use an angle between those values, and 3 pi over 4 is between those values. So I know I'm good with the answer that I just wrote. So let's put some of that together. Our radius is plus or minus 3 root 2. So let's just use the positives for a minute. If I went positive 3 root 2 and then traveled 135 degrees, or 3 pi over 4, I'm going to get to that point right there. So I know that's a good way of writing this. So positive 3 root 2, and then 3 pi over 4, or you could say 135 degrees, is a good way to write polar coordinates for this. So what would be the negative option? So what if I said negative 3 root 2? So instead of going this way and this way, what if we went negative 3 root 2? And now I still have to travel all the way around this circle to get to here. So if I am at this location right here, I know this little reference angle is pi over 4, right? Just basic degree math of unit circle. I know this is pi over 4, or you could say 45 degrees. But from here, so what would I have to add to this in order to make it all the way around to this? So if I was here, I would have to add pi plus another 3 pi over 4 would get me right here. Well, if you added pi to 3 pi over 4, what are you going to get? 7 pi over 4. Right? And so that's obviously not where we want to be. That's not the right angle. Well, sorry, it is the right angle if you started with a negative radius. Then that would be the correct way of identifying how far you have to travel. However, and this is why I said I'm really glad they gave us this, because 7 pi over 4 is too big. That's not the answer they want us to use. So by telling us this information, they're telling us, hey, don't go that way. That's too big. Instead, go that way. So from here, if I travel negative pi over 4, now I'm not only in the right location, but it also fits this domain. Right? And that's super important. So watch out for those key pieces of information like this. They're going to guide you into which answers they want you to put this in. Because as we've seen, there's many ways of writing these. And so things like this will help tell you how to write your answer. Oh, let me see this guy at the bottom here. So we are going from some polar statements to rectangular statements. So if we had a polar statement like this of r equals 4 cosine theta, and we want to convert that to rectangular form, right? And we'll peek the graph as well. But let's take a look at what's going on with this one. So 4 cosine theta. Let me take you over to here. All right. So this is what was given to us. So here's the part that gets a little tough. This is where we have to start looking at formulas and substitution that will help us to put this in a form that would be considered rectangular form. Rectangular form means get rid of r, right? So when you want it in polar form, we want it in terms of r. When you want it in rectangular form, you only want it in terms of x and y with no r in it. So the goal on this is, let's get rid of this type of information and put it only in terms of x and y. Now this is where it gets a little tough because there's multiple formulas and paths that might help you do this. And so it starts to become some recognition of what we can or can't do. And I'm going to give you a few examples to help you. So looking at this, we already know that r squared is an important piece of one of our formulas, right? We know that r squared equals x squared plus y squared. So what they said is, Well, we don't want r, we want r squared. So let's multiply both sides by r in order to create an r squared right here. Okay, so it does two things for us. One of them is, since r squared is equal to x squared plus y squared, I can make that substitution. Also, one of our other formulas said r cosine theta is x. So that was one of our other formulas that we used. And now notice I got rid of the trig function and theta. I also got rid of r, and now I have something that's only in terms of x and y. Okay, and so what they're trying to do on this is basically put it in the form of a circle. Right? They want us to put this in the form of a circle. I know we've talked about this before. Circles really look like this. This is the parent function of a circle. And we've talked about that before, and hopefully you saw that either in geometry or algebra 2. It's supposed to come in those classes. But if my parent function of a circle looks like this, let me just mention this real quick so you can see the connection. This would be a circle that is centered at 0, 0, and then the square root of this number would be your radius. If you start moving away from 0, 0, it starts looking like this. Right? And so now when I look at this, h and k represent the center of the circle when it's not at 0, 0. So that's the goal from here. As they said, hey, this does not really fit the format of a typical circle, so I don't really know how to graph this. So how can we rewrite it to look like this so that I could graph it? So what they did was they said, okay, let's just start by subtracting 4x from both sides. So they brought the 4x over to here, and then they went through their completing the square process. And I know you guys did a bunch of this in Algebra 2. Let me just throw it out there. Completing the square is figuring out what does my new c value need to be in order to create a perfect square. This is what a perfect square looks like once it's been factored, right? And the goal is to get it to look like this because this looks like this. So they said, well, if I add 4 to both sides, like they did right there, that now creates a perfect square. So when I factor it, it looks like this. And now we're looking at this model right here. And so they can say, okay, my center is at positive 2, 0. In other words, it's going to move right 2, and up or down, nothing. So there's the new center is at 2, 0. And then they said, well, okay, what about the radius? Well, if this is 4, right, remember this is something squared. So if I square root it, I get my radius of 2. So from the center, they went right 2, they went up 2, they went left 2, and they went down 2. Okay, let's try some practice. So we're going to do these on the next page so you have some room here. I'm going to give you a couple more examples. I think this will be near the end here. So yeah, should be near the end. Sorry, this one's a little lengthy, but just trying to give you guys a full description of what's going on. So again, on this one, guys, these are obviously in polar form because they involve a radius and they involve a trig function and an angle. Okay, that's not what we want. We want everything in terms of x and y so that we can get this into rectangular form. So we want to start thinking about our formulas that we have and start thinking about some substitution. So one thing we know is obviously cosecant is the same thing as 1 over sine. So we could also write this as that look right there. What could I do with this? Well, what if I multiply this over to the other side? Notice what we are now going to have. I have r sine theta equals 4. And we know that r sine theta is our y value. So I can replace that with y. And now I have the equation of a graph in rectangular form. And so now when I look at this, I recognize this is just a horizontal line. So in order to graph this, would be the same thing as to graph the horizontal line of y equals 4. Okay, so again, the goal is to get rid of this information and put it in terms of x and y. Let me jump over to this one. What could we do with this one? So what if we squared both sides? I know that within the formulas that we're using here, I like having r squared oftentimes because that's a good substitution move. I also like having r connected to my cosine value and my sine value. So what if on this one we did what we saw in an earlier problem and we said, well, let's just multiply both sides by r. So this would become r squared. This would become 2r cosine theta plus r sine theta. So that looks like a really good move because now I have formulas that sub out all three of those terms. So we know r squared is x squared plus y squared. We know r cosine theta is our x coordinate, and r sine theta is our y coordinate. So we've now written this in such a way that we have only x's and y's, and so this is considered rectangular form. The only issue is how do you graph it, right? And so if you're going to graph something like this, you really need to put it in to a format that we're used to graphing. Like obviously if I'm seeing some squared values here, I'm probably looking at a circle. And so I kind of want to get this in the form of a circle in order to do this. So let's subtract the 2x and the y over. I'm going to give myself some space because I can see what's coming here. This is what I got right now. So all I did was subtract to get everything onto one side. I'm going to do some completing the square so I can get some perfect squares out of this. Completing the square, and I'll just remind you, how do I figure out what my new c value should be? So you guys got a formula like this in Algebra 2 when you did all this completing the square stuff. So this tells you what needs to be added to create the perfect square. So if I took my b value, which is -2, cut it in half, and square it, what do you get? So -2 over 2 is -1, -1 squared is 1. So I'm going to add 1 to both sides, keep the equation balanced. Let's do the same thing on this one. So I'm going to take -1 over 2 squared would be 1/4. So I'm going to get that look right there. So now let's put this into the form of a circle. So if you were to factor this trinomial, you would be looking at x minus 1 squared. If you were to factor him, you would get y minus 1/2 squared. And if you want a little shortcut on that, like how did I know so quickly it was 1/2? When it's a perfect square, this value is always this divided by 2. That always tells you what goes right here when you put this in a factored form. On the right side, let's just clean that up. 4/4 plus 1/4 is 5/4. So we're right here. Now I could graph it. So now if I really wanted to graph a circle, I'll give you my quick ugly sketch of a circle. So I'm going to go right 1. I'm going to go up 1/2. So right 1 and up. So if there's 1, let's go up 1/2. So there's my center. And this, if I square root this, I get my radius. Now, that's going to be the root of 5 over 2, which I have no idea what that would be. So I can't graph that. I'm going to put this as a decimal so I can graph it. So about 1.1-ish is my radius. So in other words, I'm going to go about 1.1 up. I'm going to go about 1.1 to the right, 1.1 down, 1.1 left. And if I connect those dots, I got my circle. Close enough. All right. So stay tuned if you just want to see some more examples here. I'll try to go through these quickly. We're going to go the other direction on this. Okay, so now that these are in terms of x and y, this is rectangular form. I'm going to convert these back into polar form. So let's start subbing out some of this information here. So clearly looking at a circle here, my center would be at 0, positive 4, and my radius would be 4. You know, some of these you just have to start making some substitutions and giving this a shot. One thing that I know is that x squared plus y squared equals r squared, and that's a great substitution, so I'm going to expand this. So if I expand that, I'm going to get y squared minus 8y plus 16 equals 16. So a couple things we can do right now. This is obviously x squared plus y squared is r squared. So let's sub him out. I know that y is r sine theta. And if I subtract 16 from both sides, I get this. So this is really a good answer in polar form because there's no more x's or y's. It's only r and a trig function with theta. But what they like you to do on these to finish them off is to get r by itself. So that's typically the goal when we want to turn this into polar form, is to solve for r. Obviously this can be factored. Let's take out the r. So as always, if I set each factor equal to 0, I get my solutions. However, if I set r equal to 0, would that even make sense? Can you have a radius of 0? That would not exist. So I'm only going to look at this factor, and if I set that equal to 0, I'm going to get r equals 8 sine theta. And so that's the way they want us to leave those answers. What about y equals 3? We saw something similar to this up above. Now this is kind of the reverse direction of it, but we know y is r sine theta. And we get that look right. So if I replace y with r sine theta, we get this guy. Again, they want us to get r by itself. So we're going to divide that sine over to the other side. And instead of leaving sine on bottom, of course, we could move it up top and call it cosecant. And that would be the best way to leave that answer. All right, final one. Guys, I apologize for just a long lesson, but it's trying to give you full explanations here. So radar detects two airplanes at the same altitude. Their polar coordinates are 8 miles, 110, and then 15 degrees. How far apart are the planes? So this is now going to link you back to something we learned earlier, which is just really solving a triangle. So if we were to graph these guys, so here is obviously the 515, right? I went right 5 and then up 15 degrees. This guy here went 8 miles and then 110 degrees. So that's where he came from. And so they want to know how far apart are these guys. So we are solving for the length or the distance between those 2 points right there. So we're going to see this as solving a triangle. Of course, we start at 0, 0. That's how those coordinates were given, is their motion from 0. And of course, if I connect the dots here, not a right triangle as we can see. So we need to look at some real values for this. We already know some lengths, right? Because this guy is 8 miles from 0. So there's 8 miles from 0. We know this guy is 5 miles from 0. So he is 5 miles from 0. And so what about an angle here? So here's where we gotta think about this a little bit. So this right here is 15 degrees. So that's what we're seeing for that guy. So what would this angle be right here between these two airplanes? So think of it this way. If you went just this far, you've gone 15 degrees. If you go the rest of the way, now you've gone a total of 110. In other words, if I've already gone 15, how much further would I need to go in order to get this angle right here, right? So, in other words, the 110, which was the whole thing, minus this 15 degrees that we've already gone, gives me the angle between them of 95 degrees. Let's So we're given that that look right there. So the rest is, if we get a good drawing, it's just a matter of now plugging it into our cosine formula. So we got a little a squared is what we're solving for. That's the distance between the two planes. We'll just call that a, just to show what it represents. So 8 squared plus 5 squared minus 2, 8, 5 cosine 95. So that's the way we would set it up. Rest is calculator, so you would obviously type all that in. Don't forget to square root it to get a by itself, and that would give you the distance between the planes.